Welcome to Lecture 4. In this lecture, we will begin specifically talking now about quantum computing. And just as a reminder, the book is Quantum Computing, a gentle introduction and the authors are Eleanor Rifle and Wolfgang Polak. And I want to begin this discussion with a topic that follows directly from what we were discussing at the end of Lecture 3, which is the topic of orthonormal vectors. And to be more specific, what I want to do is to look at exercise 2 in the textbook. And let me just go ahead and state the question. It says, which pairs of expressions for quantum states represent the same state? And then furthermore, it says, for those pairs that represent different state, for those pairs that represent different states, describe a measurement for which the probabilities of the two outcomes differ for the two states and give these probabilities. Now, if you look at this problem in the book, you see that there are many different pairs that the book wants you to consider. It has parts A through J, so quite a large number. And I want to do one or two of these to illustrate the idea, and then hopefully after that you can do some others for our quiz. So let's first of all look at J. So this is problem 2J in your book. And the two different states that we are supposed to consider are the following. We have 1 over the square root of 2 times the 0 ket plus e to the I pi over 4 times the 1 ket. This is 1, and the other is 1 over square root of 2 times e to the minus I pi over 4 times the 0 ket plus the 1 ket. So before I say anything at all about this problem, I strongly encourage you to stop the video at this point and try to work this particular example yourselves, and then when you think you have the right answer or when you give up, then resume with the video. So stop the video now. Okay, so now we're going to work on this problem together. And keep in mind here that the first part of the question says, which pairs of expressions for quantum states represent the same state? And this is actually one of those cases. These states are really the same because the second can be obtained simply by multiplying the first by e to the minus I pi over 4. Any two states which can, or let me state it this way, anytime you have two states and one of them can be obtained from the other simply by multiplying it by a scalar, then those aren't really two different states. And here you can clearly see that if we multiply this first state by e to the minus I pi over 4, of course that doesn't affect the 1 over square root of 2 in front, and then the 0 ket gets multiplied by e to the minus I pi over 4, and for the 1 ket, when we multiply e to the I pi over 4 by e to the minus I pi over 4, we just get e to the 0, which is 1. And so indeed, just a moment's thought will show that these two states are the same. And in a case where the two states are the same, there's nothing else that needs to be done. So now let's look at another example. Maybe this time we'll look at problem C. So this will be 2C. Now in this case, the two states that we are challenged to investigate are the following: 1 over square root of 2 times the 0 ket plus the 1 ket, and 1 over square root of 2 times the negative of the 0 ket plus I times the 1 ket. Once again, just as before, I want to challenge you to stop the video at this point and try to solve this problem yourself, and then after you have finished working on it, then resume with the video. Okay, so now I hope you had some luck with this problem, but it definitely is a little trickier than the first one, a little bit more challenging, because if we look at these two states, we can see right away that these are different states. Okay, different. These are different states. And we can see that because there's no scalar by which we can multiply the first state to obtain the second state. You can see that because part of the state, the 0 ket part, has just been multiplied by -1, but the 1 ket part has been multiplied by I. And so since the two parts have been multiplied by different scalars, these two states are not the same. So now we get to the second part of this problem, and it says, for those pairs that represent different states, and that's the case we have here, describe a measurement for which the probabilities of the two outcomes differ for the two states, and give these probabilities. So what do we want to do in this case? This is an interesting question. Let me show why this is of interest. Okay. The trick to solving this problem is summarized really in just one sentence in your textbook, and this sentence is at the bottom of page 16 and continues on to page 17. So I will quote this sentence for you. The book states, for example, given a device for measuring the polarization of photons with associated basis U and U orthogonal. The state V equals AU plus BU orthogonal is measured as U with probability the absolute magnitude of A squared. Remember, that's just A times the complex conjugate of A. And as U orthogonal with probability absolute magnitude of B squared. So this one sentence gives us the key as to how we should solve this problem. And it's rather interesting because if we choose the wrong basis, it simply won't work. We'll get the same probabilities for both of these states, even though they are different states. So let me show you exactly what I mean here. I'll say if we choose the basis 0, 1, we will obtain the same probabilities even though these are different states. Now, let's prove that. Well, obviously, if we, I'll say, let's look at the first state. 1 over square root of 2, 0 plus 1. If we want to express that in terms of the 0 cat and the 1 cat, well, that's obviously easy to do. It's 1 over square root of 2 times the 0 cat plus 1 over square root of 2 times the 1 cat. So the probability of measuring zero is this number, 1 over square root of 2, times the complex conjugate of 1 over square root of 2, which of course is just 1 over square root of 2, and that's 1/2. And of course that immediately determines that the probability of the other is also 1/2, but just in case you want to verify that, so probability of measuring the 1 cat is, now we take this coefficient, but of course that is also 1 over square root of 2, so we have 1 over square root of 2 times 1 over square root of 2 conjugate equals 1/2. Now let's do the same thing for the second state, and we will see that we obtain the same probabilities. So for the second state, okay, the second state, let's go back up here. It is 1 over square root of 2 times negative 0 cat plus I times the 1 cat. And when we write that in terms of the 0 cat and the 1 cat, of course, we will get minus 1 over square root of 2 times the 0 cat plus I over the square root of 2 times the 1 cat. So probability of measuring the 0 cat is now, and this time we take this coefficient times its complex conjugate, so we would have minus 1 over square root of 2 times minus 1 over square root of 2 complex conjugate. And again, you remember, of course, that the complex conjugate of a real number is just itself, and so we get 1/2, and the probability of measuring 1 is going to be equal to this number, I over the square root of 2 times the complex conjugate of I over square root of 2, which of course gives us I over square root of 2 times minus I over the square root of 2, which gives us minus I squared over 2, which is minus of minus 1 over 2, which is 1/2. So we obtain exactly the same probabilities even though these states are not the same. And that may very well surprise you. But it also, in addition to surprising you, it gives you a bit of a challenge because remember that our task here, going back to the statement of the problem, our task is for those pairs that represent different states, which is the case we have here in problem C, describe a measurement for which the probabilities of the two outcomes differ for the two states. And so we see if we choose this basis, the 0 ket and the 1 ket, the probabilities do not differ. So we need to find, so we seek another basis. And let's just keep this general. Let's use U and U orthogonal, just the same notation that your book uses, and see what will happen if we have a general case like this, if it will help us to find an appropriate U and U orthogonal. Okay, so for the first state, recall again, the first state is 1 over square root of 2 times the 0 ket plus the 1 ket. And following the hint in the book, or not so much a hint, but a procedure, which is outlined right here, and this one quote, again, remember, this is pages 16 and 17 in your book. But following that procedure, we want to write this state as A times U plus B times U orthogonal. And now, in view of our discussion at the end of lecture 3, we know how to do this. We know that since U and U orthogonal, keep in mind now that U and U orthogonal, first of all, obviously, since U orthogonal is orthogonal to U, it is an orthogonal basis, and not only that, but any state is normal. So each one of these has been normalized. So each one of these is a unit vector. So this right here is an orthonormal basis. Okay, orthonormal basis. So this makes matters very easy because we can find A and B very easily in the following ways. So we'll say since U and U orthogonal is an orthonormal basis, we can proceed as follows. And what do? We take the inner product, of both sides of this equation, first with u, and then with u orthogonal. And you'll see why this is a good thing to do right away. So if we take the taking the inner product with u, if we do that, then we get the following. On the left-hand side, we'll get 1 over square root of 2 times the inner product of u with 0 plus the inner product of u with 1. And that will be equal to a times the inner product of u with u plus b times the inner product of u with u orthogonal. Now, why is this so convenient to do, such a convenient thing to do? Well, because remember that here u and u orthogonal, these are orthogonal vectors, which means that the inner product of these two is 0, and therefore we simply get a times the inner product of u with itself. Furthermore, remember that u is a unit vector or normal vector, and therefore the inner product of u with itself is simply 1. So we have a times 1, or a. And so therefore we immediately have the answer that a is equal to 1 over square root of 2 times the inner product of u with 0 plus the inner product of u with 1. Now, I encourage you to now do the second part yourself, where you take the inner product with u orthogonal. I imagine you can already guess what you're going to get, but I encourage you to go ahead and do this yourselves, and then we will resume our discussion. So I hope now that this was not difficult for you at all. What we will have is 1 over square root of 2 well, let's see, I guess I'll go ahead and we're already assuming here we're taking the inner product. So just to remind you here, we have, this is the equation right here, and we're going to take the inner product of both sides with u, now with u orthogonal. So if we do that, we get the following. Inner product of u orthogonal with 0 plus the inner product of u orthogonal with 1, and that is equal to a times the inner product of u orthogonal with u plus b times the inner product of u orthogonal with u orthogonal. And this is going to work very similarly to what we had before. Since u and u orthogonal are orthogonal, this inner product is 0, and since u orthogonal is a normal vector, u orthogonal time the inner product of u orthogonal with itself will be 1, and therefore this is simply equal to b just as in our previous problem up here we obtained a. When we took the inner product of both sides with u, when we take the inner product of both sides with u orthogonal, we get b. And so now we can write down immediately that b is equal to 1 over square root of 2 times the inner product of u orthogonal with 0 plus the inner product of u orthogonal with 1. Now keep in mind now, this is all for the first state. So let's summarize what we've found so far. Summary of what we have found up to this point. It was said for the first state of 2c, and that is the state 1 over square root of 2 times the 0 ket plus the 1 ket. The probability of measuring u is, now remember this will be a times the complex conjugate of a. So this will be a times a conjugate, which will be equal to 1 over square root of 2 times u 0 plus inner product of u with 1 times 1 over square root of 2 times u 0 conjugate plus u 1 conjugate. And so that is going to be equal to the 1 over square root of 2 and 1 over square root of 2 give us 1/2. And then when we take the inner product of u with 0 and multiply that by the complex conjugate of that, we will get the magnitude squared of the inner product of u with 0. And similarly, when we take the inner product of u with 1 and multiply that by its complex conjugate, we will get the magnitude squared of u with 1. But we also have cross terms we need to deal with, which will be the inner product of u with 0 times the inner product of u with 1 conjugate plus the inner product of u with 1 times the inner product of u with 0 conjugate. And that, again, is the probability when we measure the first state. That's the probability of measuring u. Now, we could go ahead, if you wish, we could go ahead and compute the probability of measuring u orthogonal, but as I stated before, to do that, all we would need to do is to multiply b by b conjugate, but after doing all the work, what we would find is then we would just obtain 1 minus this, because the two probabilities together, there's only two things that we can measure, u or u orthogonal. So the two probabilities have to add to 1, and therefore there really isn't a lot of point in going ahead and computing that second probability. So this is the probability of measuring u for the first state, and now we ask, what is the probability of measuring u for the second state? Now, I definitely hope that after what we've just done, you can calculate this on your own. So I definitely urge you to stop the video now and make a very honest effort to solve this for yourself, and then resume and see if you were right. Okay, so how do we find the probability of measuring u for the second state? Well, it's going to be extremely similar to what we've just done, but now we need to use the second state. We need to look up here at what we did for the first state. The first thing we did here was to express that first state in terms of our basis, u and u orthogonal. And we found out what a was, and likewise we found out what b was. Even though, as I argued, we really don't need b too much, because we don't have to calculate that second probability. Once we calculate the probability of obtaining u as a measurement, then we know what the probability of obtaining u complement is, or u orthogonal is. It's just 1 minus that. So we'll do the same thing down here a little bit more quickly, but not, we won't rush through it, but we'll do it a little more quickly. So recall that our second state is equal to 1 over square root of 2 times the negative of the 0 ket plus I times the 1 ket. And we want to express this as, well, in terms of our basis, u and u orthogonal. Now this time I won't compute both a and b. I'm only going to compute a so that I can compare a conjugate. See, this is the crucial thing we calculated for the first one. I want to calculate a conjugate for the second one and see how to make them different, because remember, our goal is to find a measurement, a way of measuring these so that they will give different probabilities, and also to give those probabilities. So let's see what happens now. Okay, well, again, in order to find a, take the inner product of each side with u. And when we do that, we will get 1 over square root of 2 times minus the inner product of u with 0 plus I times the inner product of u with 1 is equal to A times the inner product of U with U plus B times the inner product of U with U orthogonal. And as we know now, we've seen this a couple of times, so we know immediately that that is simply equal to A. So in this second case, A is equal to 1 over the square root of 2 times minus the inner product of U with 0 plus I times the inner product of U with 1. So this means, so for the second state, the probability of measuring U is A conjugate, which is equal to 1 over square root of 2 times minus the inner product of U with 0 plus I times the inner product of U with 1. And now we have to multiply that by its complex conjugate, which will be 1 over square root of 2 times minus the inner product of U with 0 conjugate. And then the I, when we conjugate this, the I will become minus I. So we have minus I times the complex conjugate of the inner product of U with 1. And now we have a little bit of computation to do. The 1 over square root of 2 times 1 over square root of 2 will give us 1/2. If we multiply the first terms together, the negative sign times negative sign will give us a positive sign, and we will get the magnitude squared of U with 0. If we multiply the second terms together, notice we have I and minus I, which will give us minus I squared. That's a minus of a negative 1, so that's positive 1. Times the inner product of U with 1 multiplied by the complex conjugate of the inner product of U with 1. And now, as before, we also have some cross terms. When we multiply this by this, notice we have a negative and negative, so that'll give us a positive. So we have plus I times the inner product of U with 0 times the inner product of U with 1 conjugate. And then we also have this term multiplied by this term. So we'll have minus I times the inner product of U with 1 times the inner product of U with 0 conjugate. And this is the value of A star in the second case. There's A star in the first case. Here is A star in the second case. And we want those, once again, now remember that A times A star, or A times the complex conjugate of A, that's the probability of measuring the state U. And we want that to be different for the first state and the second state in this problem. So let's now look at those. Let's summarize this and see what choice of U will work. So summary. The probability of measuring U is, for the first state, you see that right here, and it is 1/2 times the magnitude squared of the inner product of U with 0 plus the magnitude squared of the inner product of U with 1 plus the inner product of U with 0 times the complex conjugate of the inner product of U with 1 and then plus the inner product of U with 1 with the complex conjugate of the inner product of U with 0. And for the second state, that's right here above, and so we get 1/2 times inner product of U with 0 magnitude squared plus inner product of U with 1 magnitude squared plus I inner product of U with 0 times inner product of U with 1 complex conjugate minus I times inner product of U with 1 times inner product of U with 0 complex conjugate. Now, take a look at that for a moment, and let's think about whether or not we can simplify these expressions first, because if we can, then that will help us in our ultimate goal of choosing a U so that these expressions have different values. So let's stop for just a moment and think about the question of whether or not we can simplify this. If we look at this for a moment, we can conclude some interesting things that will help us to simplify this expression. Now, first of all, remember that both of these expressions arose as a result of multiplying A times its complex conjugate. And of course, A had a different value for the first state from what it had for the second state, and so that's why we get these two different expressions here, this one and this. But in each case, we took the A that was appropriate for that state and multiplied by its complex conjugate. Now, we can make some headway with these expressions in the following way. Note that A times the complex conjugate of A is real for any A, whether A is real or complex. Now, the reason that that is interesting is that it tells us that when we look at this second term here, okay, this term has to be real. Now, we know for sure that this is real because this is the inner product of u with 0 multiplied by the complex conjugate of the inner product of u with 0. And similarly, this must be real because it is the inner product of u with 1 multiplied by the complex conjugate of the inner product of u with 1. So, and keep in mind also that we can write, well, let's say this. Let's do it like this. So for the second state, we see that what's left over. We've already argued that this part has to be real, and this part has to be real, and of course the 1/2 out in the front has to be real. So that means that what is left in here must be real. So we can see that I times the inner product of u with 0 times the complex conjugate of the inner product of u with 1 minus I times the inner product of u with 1 times the complex conjugate of the inner product with u with 0, that must be real. Because, again, remember, this second expression is equal to A times A conjugate for the second state, and any number times its complex conjugate is real, so this whole expression must be real. And if the whole expression is real, well, we also know that that's real, and this is real, the multiplying factor out front is real, and therefore the remainder of this term in the parentheses must be real. So we have I times the inner product of u with 0 multiplied by the complex conjugate of the inner product of u with 1 minus I times the inner product of u with 1 times the complex conjugate of the inner product of u with 0 must be real. But that means that we notice that this expression here could also be written like this. We can factor out an I, and we get that. And that must be real. So finally, if this is pure real, then the term in the parentheses must be pure imaginary. So finally, u inner product 0 multiplied by u inner product 1 conjugate minus u inner product 1 u inner product 0 conjugate is pure imaginary. Well, after taking an additional a couple of minutes to think about this, I'm going to have to apologize because this, you're going to have to pretend that the last 3 or 4 minutes of discussion never happened, because this argument that I'm making right here, although it is, everything I've said there is correct, it doesn't seem to be very useful. In other words, I can't see how I can continue to follow along that line of thinking and arrive at a very useful conclusion. So let's continue then with what we've had here, up here in the summary. And we'll just skip this part. And again, nothing there is wrong. It's okay to use it, it's okay to look at it and to think about it, but I don't see that it's very useful. So getting back then to our summary, again, remember that in the first state, the probability of measuring the ket U is here, and in the second state, the probability of measuring the ket U is this. And what we would like to do is to find a U that will make these probabilities different. Remember, we know that if U is equal to the 0 vector, or if U is equal to 1, we've already seen that these expressions will be the same in that case. And it's easy to see why, because, for instance, if U is equal to the 0 vector, then this term right here would be 0, and this term right here would be 0. So both of these terms would drop out here in this top expression, and likewise this and this would be 0, so both of these terms would drop out of the second expression, and so the first expression would just be these terms, the second expression would just be these terms, and those are identical. So it's easy to see why, if U were only the 0 vector, that we would get the same probabilities, which is what we saw above. And likewise, with very similar reasoning, you can see that if U were simply equal to the 1 vector, again, these two expressions would be the same. And so what can we choose? Well, since it can't be the 0 vector alone, and it cannot be the 1 vector alone, let's investigate this possibility. Let's pick U to be equal to alpha times the 0 ket plus beta times the 1 ket, where alpha and beta are real numbers. I'm making that restriction to make alpha and beta real because that will make the following arithmetic much simpler. So, with this assumption, we find that our probabilities for measuring U become okay. For the first state, here's the first state, and now we're going to have the U ket to be alpha times the 0 ket plus beta times the 1 ket. So that expression will become 1/2 times alpha, and well, we'll go ahead and be careful for right now. So we'll have magnitude of alpha squared plus magnitude of beta squared plus alpha star beta plus alpha beta star. That's what we get. The way that I got that was to take the inner product. Well, basically, let's just say that I used this assumption right here for u and substituted into this expression above. But remember that alpha and beta are assumed to both be real. So this simply becomes 1/2 of alpha squared plus beta squared plus 2 alpha beta. And for the second state, we get 1/2 times magnitude of alpha squared plus magnitude of beta squared plus I times alpha star beta minus I times alpha beta star. But again, since alpha and beta are both real, this would become 1/2 of alpha squared plus beta squared plus I alpha beta minus I alpha beta. And this would simply then be 1/2 of alpha squared plus beta squared. And therefore, we see that, in fact, we can pick. So, well, remember now, what we're wanting is for these two probabilities to be different. So, these two probabilities will be different as long as we choose any u equal to alpha times the 0 cat plus beta times the 1 cat, where alpha and beta are real and neither alpha nor beta is 0. This will be sufficient, because if we see that we have seen that we obtained these expressions for the probabilities, 1/2 of alpha squared plus beta squared plus 2 alpha beta in the first case, in the second case simply 1/2 alpha squared plus beta squared. We obtained those expressions as long as alpha and beta are real, and clearly those two expressions will be different from each other as long as 2 alpha beta is not 0, which is guaranteed as long as neither alpha nor beta is 0. So this is the answer to the second part of problem 2C, that we can pick any u that satisfies those conditions. Any u satisfying that will be sufficient. And that gives an insight into how to do all of these parts of exercise 2 at the end of chapter 2. So now let's discuss some problems for this lecture. So let's now finish by looking at our problems for this lecture. And for each of these first two problems, I simply want you to circle every statement that is true. And then, as usual, the third problem will be done in class. So in the first problem, and both of these problems will be like exercise 2 at the end of the second chapter. So in the first problem, the first state is the ket 1, and the second state is I times the ket 1. A, these are the same state. B, if we pick the ket U to be the 0 ket, then these two states have different probabilities of being measured as that U ket. If we pick U to be the 1 ket, then these two states have different probabilities of being measured as U. And if we pick U to be 1 over square root of 2 times a 0 ket plus 1 over square root of 2 times a 1 ket, these states have different probabilities of being measured as U. At least one of these four statements is true, perhaps more than one is true, so you need to circle the true ones. And in the second problem, exactly the same kind of situation, except now the first state is defined here, the second state is defined here, and once again the choices A, B, C, and D are actually exactly the same as in problem 1, and again, at least one of those statements is true, perhaps more than one. You need to circle all those that are true. And then finally, problem 3 will be given in class. And so that concludes lecture 4, and good luck.